Hey, so you've watched the video, lecture video on descriptives. Now let's talk about how to do descriptives in R. So this R script is on Blackboard for you to download. And what we're going to do is I'm going to set my working directory. And that allows me to open files, a bunch of different files from the same folder. So I know where this file's hidden, so I've already set this up. But if you want to set up a working directory of your own, what you do, the easiest way, is to go Session, Set Working Directory, and tell it to choose the directory. So you would pick where you have this all of your CSV files, download it from Blackboard as well, and just click Open. That'll copy this code down here, which then I would cut and paste to the top, so I don't have to keep finding it again. Now, one thing I can also do, if your window is large enough, I have a long path here, is click this little arrow here, and that'll show you all the files that you have in the folder that you're currently working on. And so what I want to do is open my basics file. So I've called this basics review.csv. Okay, this file is the one we're using. And so I can use the read.csv function to open that CSV. Now I know in my other videos I showed you how to click import dataset from local file, click on basics review, etc., where I could tell it yes, it's a heading, you could do all this stuff. But honestly, then you have to remember to open it every single time. So really I want you to get in the habit of using working directories and at least having the code to open the document at the very beginning of your file, your basics file here. So let's add this. Let's say set working directory. I'm going to use some comments here, talk about what I'm doing. And then here we're going to be opening files. Right now I'm just going to use this basics data set. So whatever you do, get your basics data set open. It should come up over here on the right in the global environment window under data. Remember, I can click the little down arrow and look at all these different data things. This is a personality data set I borrowed from a book somewhere. Now the rest of these we're going to use a little bit later to talk about these different types of tests. So for right now, just skip it. I'll scroll down a little bit. So I can change the names of these columns in case they come through. So one thing about me working on a Mac and sometimes you working on a Windows machine is that the first column name here will just be like a garbled mess. And so it shows up usually sometimes with a little symbol. Okay. And sometimes that'll happen too if you open the CSV. Not always, but sometimes it's something about the way that Excel opens CSV files and then tries to save them as text. So don't let Excel do that. And in general, you don't need to open any of the data sets if you're using R that we're using. You just need to download them. Okay. Put them in whatever folder you want to put them in, but as a general rule, my recommendation is to not open them. So let's say your stuff is all messed up. I'm not going to run this first one right this moment because I don't have that data set open. I do have this basics data set open though. So what's happening here? It's call names. Call names is a way to change the column names. And so our basics data set here has a bunch of columns, right? And then a bunch of rows for every participant. And so what I say is call names is the function. Basics is the name of the data set. I want to change just the first column from subject number to participant number. Okay, so watch what happens. Keep your eyes glued right here. It changed from subject number to participant number. Let's say I totally screw that up and I mess it up. Because I have the data set saved in a place like the opening of the data set saved, I can just rerun my open file. It went back to being subject number over here. So another reason to have the opening of the data set right at the beginning of your file. Okay. So that's just some basic importing of files. For this example, we're actually going to use some embedded data in R that you should have used if you did the R assignment. So we're going to open up that air quality data set. So remember, I could say data air quality, and it shows up over here and it says, I promise I'm going to do something. So I'm going to hit head of air quality to give me the first 6 rows. And now it's over here where I can actually click on it and kind of look at what's going on. So remember, little NAs are missing data. Everything right aligned is a number. I can also down click here and see if it's an integer or numeric. Remember that numeric has decimals, integers do not. Now, if I want to create a frequency table, I'm going to use the table function. The table function allows me to create a frequency table of any type of data. Okay. So I just have to tell it which column I want to use. It is very tempting to type table and then the name of the data set and just hit enter. Do not do that, it will crash R. Because what it's trying to do is making you a multi-way frequency table of every possible combination of every column number. Especially don't do that when you have lots of continuous data, especially not if there's 1,000 columns. I have done this by accident. Okay. So remember, it's column name, $, data set, $, column name. And remember, that allows me to pick a particular column. And one nice thing, if you'll look down here at the bottom, I'm going to type real quick, that you can do, here I can move this up a little bit, is once you start typing the name of the data set, it will pop up some options. So I'm going to pick air quality because that's what I have open. Once you hit the $, it'll give you the list of columns. So you can just scroll down and pick which one you want. As a quick rule before we look at this frequency table, remember, do not use spaces. It will allow you to do this. I wish it did not, but do not use spaces in anything. Names of columns, names of variables, names of anything, no spaces. You can use these little dots between them or underscores or just run them all together. I know it will let you do it. Don't do it. Save yourself the heartache now by never using spaces. Okay. You also cannot start a column name with a number or special symbols. Okay. All right. So that aside, what did it do for us? Well, in this table, which is, not a very good table because frequency tables are really much better for categorical variables. But either way, it created a row of temperatures here and then the frequency for each temperature. So a row here and then the frequency here. Okay. So what that does is that allows us to look at how often each temperature happened, which, is not the best way to visualize continuous data. So let's try that for the month variable. And now this makes a lot more sense. So May, June, July, August, September, and it gives us how many times that appears in the data set, which is unsurprisingly the number of days in each of those months. Okay. So frequency tables, much better for categorical data. Categorical data. So instead, what do I do with this continuous data? Well, instead, let's talk about how to make a histogram. So histogram is the visual depiction of a frequency table. So the way histograms work is it's actually, the code is just hist. There is a function called histogram, but it's in a specific package. Hist is the one that's in R that's open all the time. I'm going to type in the name of the data set, hit the $, let's do temperature this time. Okay. It creates you a nice pretty little histogram of the temperature. Now this is clearly unimodal, but sometimes it squishes too much. So the way that you can hit zoom, by the way, to get a better view, the way that it creates these bars automatically is sometimes too few bars. And so what we can do is use the breaks function. 10 to 15 is always a good number, but play with it. It depends on the size of the data. But I'm going to go with 10 this time. And what that does is it creates a okay, well that didn't do anything. Let's do 100 and see how it looks. There we go. That visually created a difference. This would be too many. So now this just looks crazy. It has too many options. So let's go down. Let's try 20. That might be a little better. So you want something that looks like it represents a good range of the data. So 10 to 15 is always a good option, unless the range of the data is really small. 15 didn't seem to change this much. Let's try 10. Okay, that goes back to our original picture. Let's try 1 just so you can see what too few looks like. So about 10's on the bottom. Looks like it's a pretty good option. Okay. And you can that's one problem, I would say, with the data screening section you'll see and interpreting pictures is that I can make a histogram look multimodal just by changing the number of breaks. So you have to be careful here. It's an easy way to lie with statistics. All right, so that's frequency tables and histograms. Let's talk about how do I get my descriptive stats. The summary function is your best friend. Summary does so much crap for you in R, it's really great. So what we'll do is we'll do summary, and then what you do is the data set name. You can do summary of one column, but it's much quicker to do summary and then do the entire data set. What that gives you on the bottom here is, move this up some, each column, and it gives you, for categorical variables, it gives you a frequency table. For continuous or integer or number variables, it gives you the min and the max, the first and third quartiles, which is like the fourths of each one, the median, which is smack in the middle of the numbers anyway, and then the mean for each one. So really what we're going to look at, interesting-wise, is the mean for each column. And we'll also use this NAs to see how many missing data points we have. So we've got the mean for both of these. And so that's one way to get all of the means really quickly. Okay. Now I can get individual means and standard deviations and variance and standard error. So I can do this one column at a time as well. So the function for that is mean for mean. Data set name, $, column name, just like up here. And then we're going to use this little thing. Okay. So let's do that without first so you can see what happens. So I'm typing mean, data set name, air quality, $, column name, without typing this NARM thing. And it tells me that the temperature mean is 77. Okay. So it ran just fine, because there are no missing data points in temperature here. Now let's try that for ozone and see what happens. So here's a trick. If you hit the up arrow, it will copy the last thing that you, or paste the last thing that you typed, so I can just back up here, type ozone. There we go. So then it figured it out. You can also hit tab to fill in, especially if you have long variable names. So watch what happens on this one. Okay, it gives me an NA. Well, shoot. And so the reason that happens is because I have missing values. And so it won't give you a score because it's not sure what you want to do with those missing values. So the solution to that is to use na.rm, so that's na remove, question mark. Like, should I remove NAs? And you have to type T, or you can type the whole word true. Either way, it should turn blue. Okay. Blue thing means it's a reserve word, so you don't name a column name T as well. Or F. So try not to use reserve names or function names for different things, because it can cause you some very interesting problems. Okay. So if I did my exact same thing I did a minute ago, so my ozone thing, so I hit the up arrow, comma, na.rm, and then true. So to make that type out for me real quick, I hit tab. Now I've got my 4212. So the nice thing about the summary function is that it deals with NAs for you kind of quickly, but it only shows you as many decimals as it sort of wants to show you, because you will see that each one of these columns is a different number of decimals, whereas here I can get a more precise number. Okay. Now that setup, dataset, $, column name, comma, na.rm equals true, works for pretty much everything we're going to cover in this lecture. Okay. So all we have to do now is change this thing in the front. So variance, VAR, is calculated using this function. It's the variance of our, okay, I'm sorry, let me go back. The average temperature is 78 degrees, and the variance, the squared distance from the mean, is almost 90 degrees. So that doesn't make just a whole lot of sense. That would be like -10 to some unreasonable temperature. So squared distance from the mean is not so useful, so let's calculate standard deviation. Okay. And standard deviation indicates it's about 9.5 points. That makes a lot more sense. Because if I look at the picture over here, it's clearly not going below 0 or above 160. Instead, it is about 10 points on either side is where the majority of the data is. Now, how to calculate standard error? Well, there's unfortunately no standard error function in base R, meaning you have to do it yourself mathematically. So what I'm going to do is I'm going to take that standard deviation function I just did. I'm going to divide by the square root. So the square root function is sqrt of n. Okay. And so what we've done is taken SD divided by the square root of n. Okay, this won't run at the bottom. I'm just showing you what mathematically I'm doing. What is n? N is the number of data points in that column. So I could look at it, say it's 153 observations. Now the problem with that is that is going to give me with NAs if I just type in 153. Now temperature doesn't have any NAs, but if another column did, I would have to remember like, oh right, this ozone column only has 153 minus 37. So I'm going to try to get you to not use typed numbers if you can help it. And so instead we're going to make R do it for us, and we're just going to tell it, give me the length of air quality temperature. Okay. So it tells me that the length is 153 data points. But if I did here, and I hope I'm not wrong here, it'll be kind of embarrassing. Okay. Oh, shoot, I am wrong. So this does not work well for NAs, and I probably shouldn't teach you this. Let's see if we can do. Nope. Interesting. Let's do this. Let me teach you something better. Okay. So what I did was added a little function here, and let's see if this works. Doing things on the fly. So NA omit is a function that will omit NAs that exist. Okay. Let's do temperature, and we know temperature doesn't have any NAs, so we should get 153. Okay, and we did. Let's try the same thing again with ozone. And I got 116, which should be 153 minus 37. Ah, that's better. Phew! Okay, let's dodge this bullet. So we're going to use the length of only the valid ones. So NA omit, like I said, is a function that just like says, okay, ditch all of the NAs. Length is a function that tells me how long something is. It's very tempting to do length of air quality and just call it a day. But remember, each column has a slightly different number of valid data points, so no missing data. And the length function of a data set actually does something weird. It gives you the number of columns. So that's why we're including the specific column we're interested in addition to the fact that we're interested in making sure that the number of data points is correct on the bottom here. Okay. So we're going to take the square root of n, which is how many not missing data points we have. Okay. So it kind of looks a little crazy because if you're brand new to R, this is a lot of functions at once. But just kind of keep some notes for yourself, and we also have an R documentation on Blackboard. So NA omit is it'll delete all the missing data. Length is calculate how many points there are left. Square root is the square root function, and that is n on the bottom. Okay. So what is the standard error for temperature? And it's 0.77. Okay, because we're dividing by square root of 153, and so that is much smaller than the standard deviation of almost 10 points. Okay. So remember, standard error is our estimate of the population standard deviation. So we expect the actual temperature to only vary by about 1 point on either side, from 78 degrees. Now, the next thing we're going to do is calculate skew and kurtosis. Now, you need the moments library for this. If you did not have that library, click on Packages, click Install, type in the word moments. You do have to be on the internet for this to work, and then click Install. And it's going to be mad at me. It's going to do some installation down here at the bottom for you. I already have this installed. Okay. Also, something that you will do 100 times until you've used R a lot, and then you'll only do it about once every day, is that you'll open a package, or you'll install a package and forget to open it. Okay. So the most common thing we're going to ask you in the help when you're having trouble, it says this function not found. Be like, did you open the package? Probably say that about 10 times a day when I'm teaching in R because it's very easy to do. Okay, so you can click on it over here. So I'm going to scroll down to moments, methods. Here's moments, so I can click on it over here, or I can remember to put it in the data set. Okay. While these are both very handy things over here to have, I always type it in the data set so I don't forget to open it as I'm going. The function name for Skewness for Skew is Skewness, not just Skew, but Skewness. Okay. And look, it works exactly the same as mean, variance, standard deviation. So we got the RNA.rm code. So let's see, the skew of the temperature variable, let me go back and look at the plot, is slight negative skew. So you can see that by there's a little more over here than over here, but this is pretty close to normal. The kurtosis is kind of high. So that means that it is squished up more than normal. So positive number for kurtosis here means it's a leptokurtic distribution, which means it's squished in a little bit from normal. It's taller than normal. Negative number would be platykurtic or flatter than normal. Okay, so lower than normal, whereas leptokurtic distributions are higher than normal. Okay, that makes sense, unlike the skew thing. Okay. All right, so that's where we'll stop for this video. The next set of videos will cover t-tests, so get excited.